So now we're going to look at work. Now, work is, we're not going to spend nearly as much time on it because, as I said before, right, we're going to set up a lot of our systems so that we can essentially ignore work. So no work is done. Now, but of course there are chemical reactions that do involve work, right? And these are mostly reactions where we see gas expansion, like we talked about in the internal combustion engine, right? So where we produce a lot of gas in a reaction, that reaction has the ability to do work. Now, most reactions that we look at are not producing large quantities of gas, so essentially work is zero, and we can set it up to minimize or to actually make work zero. But let's look at it a little bit. So work is simply a volume change against an internal pressure, or at least the type of work that we're going to be working with or looking at in chemical reactions, which is called PV work or pressure volume work, where we have a volume change against some external pressure. And so we have work equals negative external pressure times delta V. Now, why negative? Well, remember our sign conventions where negative work, right, is equal to work done by the system, right? And so that's what we're going to focus on. So, right, so it's going to be work done by the system, so it's negative. Now, we want to express typically work in joules, right? So we have this sort of useful conversion here because notice what our units are going to be, right? Pressure is going to have to be in atmospheres. Volume is going to be in likely liters or some version of that, so we can put it into liters. So we're going to have often get our work units in atmosphere liters, but we want to be able to express it in sort of conventional energy units. So we have this conversion of 101.3 joules is equivalent to 1 atmosphere liter of work. So let's look at it here. A balloon is inflated. PV work is done, right? So when you inflate a balloon, you're changing volume against some external atmospheric pressure, right? To get that balloon to blow up, it has to go against the atmospheric pressure. If the balloon is inflated from 0.1 liters to 1.85 liters, and the atmospheric pressure is 1 atmosphere, how much work is done in joules? Okay, well, let's just start it here. So we got work is equal to negative. Our external pressure here is 1.00 atm. Our delta V is again final minus initial. So this is going to be our delta V is going to be V final minus V initial. So our final is 1.85 liters minus 0.1 liters. So we got equals negative 1 atm times a change of 1.75 liters. So this is not too hard here. Work is going to be equal to negative 1.75 liter atmospheres. Now, if we do our units conversion, we can end this by 1 liter atmosphere, 101.3 joules. So if we do this conversion, 1.75 times 101.3, we get negative to 3 significant figures. Oops. Negative 177 joules would be our work. So work is equal to negative 177 joules for this particular example, right? So to blow up this balloon, it took, or negative or 177 joules of work was done by the system. Right? The system here being, right, the gas. Okay, so that's work. Now, again, we are going to do all that we can to minimize work in almost every example that we look at. So let's look at our first sort of real-world application. This is something called constant volume calorimetry. So this is a particular type of calorimetry. We will look at constant pressure calorimetry in a later section, which is more common than what you'll actually look at when we do a lab on calorimetry. But constant volume calorimetry is a special kind of calorimetry where we are looking at how much energy is given off when essentially we burn something. So we do it in a specialized piece of equipment, and this is why we don't do it a lot in lab. These are, expensive, hard to maintain sometimes, expensive pieces of equipment, which is called a calorimeter, or more particularly a bomb calorimeter. And it contains of sort of two cases. We have the internal, what is called the bomb, where our sample is contained. And it is surrounded by a secondary container that is filled with a given amount of water. And we can look at the temperature of that water, and that's really what we're going to study. So now, what we want to sort of focus on here is the sample here is our system. Right? Remember, very narrow defined. Everything else, the water, the container, right? This is the surroundings, or what we're going to call here the calorimeter, right? The calorimeter is our surroundings. The sample is our system. Now, remember when we talked about our equations, right? When we first introduced heat, we introduced sort of this basic equation of Q equals C times delta T. Now, this equation is appropriate for this particular type of calorimetry, and this is really the only place where we use it in this chapter, because we are not dealing with, we don't have to worry about, like we did in the previous examples, where we have a certain material and we want to be able to use specific masses or different masses of that material. Here, we're simply looking at the calorimeter. The calorimeter is a piece of equipment. It has a constant mass, and so we don't need to worry about that. We just need to measure a heat capacity of this material or of this piece of equipment, and we can use that every time we use this calorimeter. Now, remember, the calorimeter here, this is our surroundings. So the basic process here is we are going to calculate the Q of the calorimeter, right, using its specific heat and how much the temperature changes by, and we're going to use our system surrounding relationship, right, that the Q of the calorimeter or the surroundings equals the negative Q of the reaction, or the system, right? So equal but opposite sign. And notice we say that the energy is equal to the negative Q of the reaction, right? Now, why is that? Well, I'll remind you here, let's do it down here, that I just said that, or I said earlier, that the energy equals Q plus W. But we just said that W equals negative P delta V. Now, this is constant volume, right? So there is no change in volume. There is no work being done here, right? There's no change in volume. So in this case, work equals 0. So this is why we can say that delta E is simply equal to Q. Or in this case, right, our Q of reaction. Now, don't worry about the negatives in here. It's just the another way to think about this is just the delta E of reaction, or the system, is equal to Q of the system. The negative Q of reaction follow from this equation where it's the opposite. So here the negative just means the opposite of the calorimeter, whether it's actually positive or negative depends on what the calorimeter is going to be. Now, for these types of problems, it's always going to be a negative value because we're always going to be releasing energy from the system because we're burning these things. And the surroundings are going to be gaining or absorbing that heat. Okay, so let's go back to a specific problem here. So we have our energy of the system is going to equal Q of the system based on what we just said. We've talked about that our calorimeter has a constant volume and we can measure delta E for these combustion or burning reactions. And so we have a constant heat capacity. So we just need to know what that heat capacity is. So let's apply it to a problem here. So we have 1.550 grams of hexane, and we want to undergo a combustion in a calorimeter. The temperature changes from 25.87 to 38.13, and we want to find the delta E of the reaction. Okay, so as with a lot of calorimetry problems, we cannot do the reaction directly, right? And this is because it's really difficult to monitor the actual temperature change of the molecules that are reacting, right? So we almost always will monitor the surroundings and apply that to the system because of our relationships that we know. So we're going to start by looking at the surroundings, or in this case, the calorimeter. So let's look at our Q of the calorimeter here. So we need to know the specific heated calorimeter, which is given here. Okay. 5.73 kilojoules. Notice the units per degree Celsius. Now, what's my delta T? So my delta T, right, is my final 38.13 degrees Celsius minus 25.87 degrees Celsius equals 12.26 degrees Celsius, positive, right? So we simply do our math and we get Q of the calorimeter equals 70.25 kilojoules. So our temperature units cancel and we get our Q of the calorimeter. So in other words, the calorimeter gained 70.25 kilojoules of heat. Now, what about the reaction? Now, remember, the Q of reaction is going to be the opposite of that, so negative 70.25 kilojoules. So while the surroundings, the calorimeter gained 70.25 kilojoules, that means the reaction must have given off 70.25 kilojoules. And then finally, the change in energy, which is what we want to find of our reaction, is simply equal to the Q of our reaction. So right here, so it's going to be equal to negative 70.25 kilojoules. Now, that's not the end of our problem, of course, because if you look closely, they want us to find the change in reaction in kilojoules per mole of hexane. So this is the total amount given off when we combust 1.55 grams of hexane. But a lot of times we'll standardize things to per mole of hexane, so then we can look at more comparative things. So we could compare, burning some amount of something else by, we don't have to use exactly the same amounts, but if we can compare them on a per mole basis, we can see, oh, this gives off this much per mole, this gives off this much per mole. So how do we do that? Well, first of all, we have to know how many moles we have. So if we take 1.550 grams, we need to know the molar mass of hexane. Okay? So molar mass C6H14 equals 6 carbons plus 12 hydrogens. If we add all that together, we get 86.34 grams per mole of hexane. So if I take the 1.55 I get 0.01795 mole of hexane. So now I can come up here to my value. And so I have kilojoules per mole. Okay. So divided by 0.1795 moles of hexane. And we get a delta E that's equal to negative 3914 kilojoules per mole of hexane. Now, properly, we could leave this probably as 4. It's probably fine, be giving our mass was 4. Significant figures. So this is going to give off 3,914 kilojoules for every mole of hexane we burn. That's quite a lot, right? Hexane is something that has a fairly high chemical potential energy, right? So these numbers that we're calculating here go back and give us sort of information about, what kinds of materials have high chemical potential energies, right? The more heat they give off, the more their energy changes, right? When you burn them, the higher the chemical potential energy is. All right, so we're going to bring this section to a close. Next time, we're going to introduce another concept called enthalpy.